Hello folks, this is Sridhar Ramakrishnan and welcome to our webinar this month. I guess before we get started, a few bookkeeping items. The presentation by Hari Viswanathan will begin shortly and will go on till approximately 1 p.m. And as in previous webinars, Hari has consented to stay on for a little longer to engage in any question answers that people might have, and we thank Hari for that. The slides and the recordings, this session is being recorded. Shortly after the webinar, both the slides and the recording will be available on our YouTube channel at youtube.com/millibotv, or you can connect to it from the events page at the website at millibo.com. Please keep your telephone or your microphone muted at all times. If I unmute everyone, there's basically, if there are sounds of your cell phone ringing or you typing on the keyboard, etc., that becomes very distracting. So please help by keeping your microphones and your telephones muted at all times. Unmute yourself if you need to ask questions. If you dialed in and you haven't entered your audio pin, please remember that there's no way for me to unmute you from the system. Okay. By the way, you can always ask questions by chat. If you have questions and you prefer to ask it by chat message, then send me a chat message and I'll relay that to Hari. Let's see. I think that's about it. So, okay, with that, let's get started. Today, we're delighted to have Hari Viswanathan to talk to us about demystifying mobile grid computing. Hari actually sent me the slides a little earlier, and as I was leafing through it, looks like a fascinating topic on which some great research has been done by Rutgers as well as Hari. So I'm really excited to have him give us a talk. Hari is actually a PhD candidate in the electrical and computer engineering departments at Rutgers University. His research focuses on autonomic management of distributed computing systems with applications ranging from mobile grid computing to data center management. During the summer of 2012, he worked as a research intern with the Next Gen Systems and Smarter Planet Solutions at IBM Research Labs in India. He also spent the summer of 2013 as a research intern in the Mobile Networking and Communications Group at NEC Research Labs in Princeton. His research work and results have been published in prestigious conferences and journals. His work on thermal-aware autonomic management of virtualized data centers received the Best Paper Award in IEEE HIPC 2012. He obtained his MS in ECE also from Rutgers in 2009 and his BE in ECE from PSG College of Technology in Coimbatore, India in 2006. With that, I'm delighted to have Hari present this talk today. Please take it away, Hari.
Very good afternoon, everyone. Thank you, Sridhar, for the introduction. So let me begin with a brief outline of the talk today. First, I'll present the case for mobile grid computing, how the solutions for mobile grid computing should look like, and the potential applications. Then I'll move on to discuss the research challenges and related work done in this field of research. And we'll go into details about our specific research contributions. One is an autonomic middleware for mobile grid computing, and the other is an uncertainty-aware resource management framework which builds on top of the autonomic middleware. Finally, I'll conclude with future directions and my ongoing work at Rutgers. So the mobile computing revolution is characterized by two diverging trends. The first is the tremendous improvement in the sensing, computation, and communication capabilities of mobile handheld devices, which owes a lot to the significant advances in microprocessor storage, sensing, and communication and wireless technologies. This is mainly driven by enriching the need to enrich user experience, mobile user experience. The second trend is the growing popularity of cloud computing with a focus on light front-end and heavy back-end. So these two diverging trends leads us to make, leads us to make the following observation, which is mobile devices are underutilized on average, which opens up tremendous possibilities. The possibility here is that the heterogeneity or the heterogeneous computing, sensing, and communication capabilities of these mobile devices can be exploited for novel collaborative data and compute-intensive ubiquitous mobile applications. So why collaborate? Real-time in-the-field data collection and processing is challenging on individual mobile platforms. That's simply because of insufficient data in an individual mobile device. For example, if you want to derive contextual information regarding what a person is doing, then you need information from heterogeneous sensors from multiple sources, and in-network processing needs to be performed for that. The second reason is insufficient sensing and computing capabilities at one device. Sometimes the capabilities of the device may not be sufficient to perform compute-intensive signal processing, which may be required. One might wonder, why not the traditional cloud or grid computing approach? Why don't we use that to collaborate? The reason is that the prohibitive cost and response time involved in this approach. So how else do we collaborate? Mobile grid computing offers a fascinating opportunity. So mobile grid computing is characterized by network mobile devices collaboratively processing massive amounts of generated sensor data in the field. And any solution for mobile grid computing should have provisions for automatic service discovery without any human intervention. It should have provisions for definition and execution of mobile application workflows in real time and in the field. By workflows, what we refer to here is the data processing chains, which are the computational tasks and their order of execution. Yes.
Can you just go back to your previous slide? So in the last bullet, can you say more about that? What is that? I guess when you mean the traditional approach of wired grid and/or cloud computing, what exactly are you envisaging there?
Oh, what I'm referring to is just leave the data collection in the field and do all the processing in the cloud or the grid. So mobile grid computing differs from this approach, where the processing is also done in the field, real-time, in situ. So when
I see.
Yes.
Is the processing only done in situ and in the field, or is it hybridized and split between the field and the cloud?
There is a provision to split between the field and the cloud, but today I'll focus on what we'll have to do if things have to be done in the field.
Okay, thank you.
Yeah. So we've seen what any solution for mobile grid computing should have provisions for. Just to quickly recap, it should have provisions for automatic service discovery, and we should be able to define and execute mobile application workflows real time, and all this should be done in a transparent manner. The end user should not be involved in all of these processes. Some fascinating mobile grid applications or potential mobile grid applications include ubiquitous healthcare, real-time rainfall and flood risk estimation. I'll just talk about these two applications in a bit more detail in the next slides. Other applications include pollution level estimation using real-time air quality measurements and distributed target recognition and tracking. So when I say mobile grid computing can enable ubiquitous healthcare, what I mean is data sources or sensor modes attached to the patients can capture vital signs such as electrocardiogram, blood pressure, electromyogram, and other kinematic information like acceleration and angular velocity can also be obtained from the data sources attached to subjects. And the computing resources or the underutilized computing resources in the vicinity can be used or exploited to work on this data and extract valuable information about psychophysiological condition of the patient or the subject. And this knowledge generated can be either stored in health record databases, or it can be used to send automated alerts to doctors, or it can be used to send alerts to emergency medical services. One might think, okay, this is not absolutely necessary in a civilian scenario, but if you take the example of a military scenario where immediate access to cloud or grid-based computing resources is unavailable, then mobile grid computing comes in handy. The second example here is ubiquitous rainfall sensing and flood risk estimation. So currently the way rainfall estimation and flood risk estimation are done is using weather radars, and this is at a very low granularity, as in the knowledge or the information generated is very coarse. So scientists have come up with ways to augment data from weather radars with data from ubiquitous rainfall sensors such as the tipping bucket sensors and the windshield wipers available in most of the new cars. And they have developed new models which fuses all of this data together to come up with rainfall estimates and flood risk estimates in a particular geographical locality. And mobile grid computing allows us to process this data from disparate sensor sources real-time in situ to enable rainfall and flood risk estimation. So when I mentioned mobile grid computing, some of you might have wondered, okay, this sounds very similar to mobile cloud computing. I've heard of that before, and what is the difference between mobile grid computing and mobile cloud computing? So mobile cloud computing, or MCC, again, aims at code offloading but it is done mainly to immobile elastic resource pools, which might include public or private clouds and small dedicated computing resources, also called cloudlets. Recently, researchers have tried to extend this definition of mobile cloud computing to include mobile devices in the elastic resource pool. The similarity here is both mobile grid computing, as I refer to it, and mobile cloud computing are aimed at enhancing computational capabilities of mobile devices. But there are reasons why we prefer to call it a mobile grid rather than a mobile cloud, because the volunteered mobile devices in the field do not belong to the same organizational entity in most application scenarios. Also, these devices are loosely coupled over local area networks and wide area networks, unlike tightly coupled cloud entities. That's why we refer to them as mobile grids and mobile grid computing rather than mobile cloud computing. So let me move on to the research challenges in the field of mobile grid computing. They are efficient resource discovery, as I've already mentioned, with minimal human intervention, and efficient resource provisioning. By efficient resource provisioning, what I mean is task allocation. We were talking about workloads, mobile application workloads. So how do we assign the different tasks in these workloads to the different mobile devices in an efficient manner? So when we think about task allocation, specific solutions need to be developed for data parallel applications and task parallel applications, which are fundamentally different. Data parallel applications refers to applications where huge mass of data is chunked and it's given to different parallel computing nodes so that they can perform the same data, they can perform the same task on these chunks of data and aggregate those individual results to generate the final result. That's what we mean by data parallel applications. Whereas task parallel applications are different. Their parallel computing nodes may perform different tasks on different data at the same time. And we'll take a closer look at task parallel applications in the second half of this presentation. Apart from efficient resource discovery and efficient resource provisioning, the third major research challenge is uncertainty awareness. The first two are relatively easy to understand and relate to, whereas the third one, uncertainty awareness, is a bit more tricky. So when we talk about uncertainty in the mobile grid computing environment, they can come from multiple sources. They can either come from computing resources. If we have inaccurate estimates of the availability of computing devices, then that can have an adverse effect on the timeliness of the results generated. Uncertainty again can come from the quality and quantity of data, which we refer to as data uncertainty, and this has a bearing on the accuracy of the final result generated. And finally, we have what is called as model uncertainty, in the sense certain computational models behave differently or unpredictably in terms of execution time and accuracy of the result depending on the input data. So these any mobile grid computing solution should be aware of the uncertainty arising out of these three sources. So let me just point to some works that have been done by other researchers in the field of code offloading, mobile grid computing, and uncertainty management, and try to distinguish our work along the way.
Sorry, a question has come online.
Yes.
The question has to do with the quality, the data quality. The questioner says, but it looks as if the data quality issue is sort of independent or orthogonal to mobile grid computing. Is that correct?
Not exactly. So data quality and quantity, it works together with computing resource uncertainty. So it just doesn't mean that, okay, if you have a large quantity of very good data, you are guaranteed to have good results. No. You can, it could be affected by lack of computing resources in the mobile grid environment. Similarly, if you have a lot of computing resources at your disposal, it doesn't mean that you can give guaranteed good quality results back to the user, because you might be lacking good quality data. So there is an interplay that's going on there, which should be a bit clearer, I hope, in the future slides. But it's not an orthogonal problem. It's closely tied to the problem of executing mobile application workflows in the field real time.
Okay, thank you.
Yeah. So let me just proceed, and we'll come back to that point later. So if the question still persists, we can ask. Okay, so the first works on code offloading, also called as cyber foraging. They just dealt with offloading expensive tasks to the cloud in a manner which is transparent to the end user. This of course results in significant battery savings at the mobile device, but at the cost of significant energy footprint because of the dedicated cloud. And it suffers from the bane of extreme centralization, and also the huge communication costs for the user, the wireless provider, and the application provider. So the other extreme of cyber foraging is opportunistic computing, which is which solely exploits opportunistic communication between pairs of devices to exchange data and resources, or to share data and resources. And this comes under the bigger research area of delay-tolerant distributed computing. But again, opportunistic computing solely depends on direct encounters. It's highly unstructured, without any provisions for defining mobile application workflows that will allow a number of application developers to design applications for mobile grids. And again, opportunistic computing have little or no uncertainty management built into it. There have been some efforts to include the mobile devices into the mobile grid, into the grid or cloud computing framework, but those were mainly done keeping in mind, that mobile devices will just serve as service requesters and not as service providers or data providers as such. The way we differ from these works is that we have multiple roles for mobile devices. They can be service requesters, service providers, data providers, brokers, and so on. And we have uncertainty management built in, and also have self-managing capabilities, which the existing solutions lack. So finally, coming to work on data uncertainty management, some researchers tried to handle this problem of data uncertainty in isolation, with the aim to capture limitations arising out of imperfect or partial data so that they can improve the accuracy in the results. Same was done by a bunch of other researchers focusing only on resource uncertainty management, and their aim was to capture the limitations arising out of insufficient computing resources to ensure the timeliness of the result. But we have to remember that both the accuracy and timeliness are important for an application or an end user. And if we don't take care of the uncertainty arising out of either data or resource uncertainty, then they may propagate up the data processing chain and have an adverse effect on the relevance of the generated result. So what this observation makes it clear that there is a need for joint data and computing resource uncertainty aware solution for mobile grid computing, which is what we'll be focusing on. So let me just move on to our main contributions. The first one is an autonomic middleware for mobile grid computing, and the second one is the uncertainty aware resource management framework. To make the uncertainty aware resource management work, we need self-managing middleware for mobile grid computing to harness the heterogeneous sensing, computing, and communication capabilities of different devices in the field. And let's first take a look at our work on autonomic middleware for mobile grid computing. So what we propose is a role-based architecture where the mobile devices can play one of the many following roles. Service requesters, which plays request for additional computing or resources or data, and data providers and resource providers, which are self-explanatory, and together we refer to them as the service providers. And there are these special service providers also called as arbitrators or brokers, which handle these service requests coming from the requesters. They identify the data and resource providers to give the tasks to, because data providers provide the data and the resource providers process the data. And the arbitrators then collect the results, aggregate the results, and give it back to the service requester. So as I said, to reiterate, the mobile devices in the grid can at any time play one of these four roles. The autonomic middleware that we are proposing, yes.
Is the arbitrator also a mobile node, or is that actually a centralized cloud service?
No, the arbitrator in our current prototype is a mobile node again, and it can be moved to the cloud or a cloudlet. So the solution is kept generic in the sense that there are many pieces in this solution which can be moved to the cloud. And you can make a gradual transition to mobile cloud computing. So here we deal with what we do when everything has to be done in the field. So the autonomic middleware, as I said, is self-managing, which means it has self-organization, self-optimization, and self-healing capabilities. And you need these self-managing capabilities to efficiently harness the heterogeneous resource pool that is lying underneath. So the mechanisms that impart the self-organization capabilities to this autonomic middleware are arbitrator self-election, in the sense how do certain nodes decide to become arbitrators, or how are arbitrators elected in the field, and how do devices advertise themselves and make themselves available to other devices. That's made possible by service advertisements, and uncertainty awareness. All these three impart the self-organization capability to the autonomic middleware, and an efficient resource provisioning engine, which we have designed specifically for data parallel applications in this work, imparts the self-optimization capability. What happens in the case of task parallel applications is something which we'll take a look at in the second part of the presentation. And then self-healing mechanism, which is very important for handling failures, is imparted through application waypoints. And we also have over and under provisioning alerts for ensuring application quality of service even under uncertainty. So we'll take a look. Yes.
Will the concept of service discovery and leader, I guess, arbitrator selection being done by the mobile nodes themselves, will that lead to, lots of traffic, administrative traffic while this takes place? And can you comment about that overhead?
Yeah, so that's what I'll be talking about in self-organization. So service discovery is done periodically. So that is going to result in some form of overhead, but this overhead is in no way different from the mobile traffic, which is anyway generated by a host of many applications that sit on our mobile devices. And if a bunch of applications are bundled together under this mobile grid computing paradigm, then in fact the service discoveries, the service advertisements would be done for a host of applications, and it would only result in fewer mobile traffic than what we have today. That's about service advertisements, which is pretty straightforward. But the question about arbitrator self-election, it's much more tricky because it's a non-trivial challenge. As Sridhar pointed out, it's if we have too many arbitrators, then yes, there is robustness in the face of some arbitrator failures, but the con or the disadvantage is that there are a number of small resource pools and there is excessive control overhead. But on the other hand, if we go for very few arbitrators, the advantage is that we'll have large resource pools, and but the disadvantage is that it may compromise the robustness when arbitrators fail. There is no failover arbitrator to look up to. So this arbitrator self-election mechanism that we have implemented in our prototype is heavily inspired by our work on distributed adaptive sampling in sensor-based autonomic systems, where we were faced with the problem of distributed representative self-election, and the algorithm for arbitrator self-election mimics the solution that we developed for sensor-based autonomic systems, and I would be glad to discuss this solution in detail offline because it's out of the scope of this presentation, the specifics of this particular algorithm. When I was referring to uncertainty awareness within self-organization, what I was referring to is do arbitrators believe the service advertisements fully? So when a person with a mobile device walks into a coffee shop, the mobile device might tell the arbitrator that I'm available for the next 3 hours. But it might be based on battery drain estimates, and it does not capture the effect that the owner of the mobile device might walk out of the coffee shop in 5 minutes. So what we came up with is the arbitrators, which change over time, they maintain these long-term statistics about service provider dynamics at a given locality. So we should not mistake that, okay, this knowledge just stays with a particular arbitrator and it dies with it. No, this is maintained at a particular locality. So when arbitrators change over time, this knowledge is passed on. So what do we mean by these long-term statistics? Some things that can be easily maintained are the average joining rate of service providers at that particular locality, which just a join is the first service advertisement that you ever hear from a service provider. That event is what we call a join. And it's easy to keep track of the joining rate of service providers at a particular locality by an arbitrator. And it's easy to keep track of the average availability duration of a particular service provider. Again, the time difference between the last service advertisement and the first gives you this number. And maintaining these two long-term averages gives us an idea about the number of service providers, average number of service providers available at a locality. And the relation between these three variables is governed by Little's theorem, which is a cornerstone of queuing theory. So what do these statistics help us do? First, they decrease the reliance on service advertisements, And the knowledge of these three statistics gives us an idea of the churn rate of service providers at a particular locality, the rate at which service providers join and leave. If we know that, then we can avoid giving too many tasks to a node that is going to leave anyway, and which would lead to a lot of task migrations. We can avoid that. So that's what we mean by uncertainty awareness in the context of self-organization. Moving on to self-optimization. Once we have dealt with the problem of resource discovery and uncertainty-aware self-organization, then comes the problem of how do you split tasks amongst the service providers in an efficient manner. And what do we mean by efficient? So efficient can be minimizing the battery drain when at all service providers, or minimizing the total response time for a user. So the arbitrator in our solution is composed of two components. One is a workload manager and the other is a scheduler, or the optimizer. The workload manager tracks the requests. It is responsible for allocating workload tasks among the service providers and aggregating results. It's just sort of the bookkeeper. But the optimizer is the more intelligent component, which identifies the number of service providers, and it determines the optimal distribution of workload tasks. So what do we mean by an optimal distribution of workload tasks? As I said, our aim could be to either minimize the battery drain at the service providers or minimize the response time. But if we were to minimize the or maximize the minimal residual battery capacity, which is the other way of looking at it, you don't want any device to drain a lot of battery in the process. If that's the objective, then this is a sort of an optimization problem that the arbitrator would solve to achieve that purpose. So this is what the self-optimization capability entails. So we built a small prototype of 10 devices to test our mobile grid computing framework with the autonomic and in particular the autonomic middleware. So this heterogeneous resource pool consisted of a tablet, 4 different types of smartphones with different computing and communication capabilities and battery capacities, and Linux-based laptops and notebooks as well. And the way these devices communicated was through a scalable content-based coordination space called Comet, which was developed by our colleagues at Cloud and Autonomic Computing Center at Rutgers. I'd be glad to discuss about this as well offline. So to test our solutions, the first thing we need is an application. We need a distributed data parallel application, and we have to profile the tasks in the workload corresponding to that application. So we took the example of distributed object recognition. To be specific, we took appearance-based object recognition, which involved creating eigen-face representations of images, storing them in a database, distributed database, and then getting an image. So a user submits an image and asks the system what it is, and the system compares that image with the data, images in the database, and comes up with the solution saying it's a book, or it's the Statue of Liberty that you're looking at, or it's a bottle, or something like that. So that's what this application looks like. And the fundamental operation in this application is matrix multiplication, and that's the task we were interested in profiling. So by profiling, what I mean is how much battery does this task drain, and how much time does it take to run at a particular mobile device. We need this information to be able to do optimal resource allocation. That's why we do device and application profiling. And as you can see here, we ran 76 of these fundamental tasks, and we observed the current drain and the voltage drop. The voltage didn't drop much. It's the current drain that we were interested in, and that helped us calculate how much battery drain this particular workload task incurs. And as you can see, the laptop was the most efficient in terms of workload completion time, and the slowest phone, the smallest phone, was the worst in terms of workload completion time. And it's very easy to appreciate that if the phone was to do everything by itself, then the result would be available in 10 minutes, which is not even close to near real time. So if you want near real time performance in the field, then mobile grid computing is the solution, where you have to harness the computing capabilities of other devices in the vicinity. So to test the self-optimization feature, here when I refer to optimization, I refer to minimal battery drain at different devices. What we did was we tested it against other scheduling policies, round robin and first come first serve. What's apparent here is, okay, so the metric, let's talk about the metric. We looked at the fairness index in terms of battery drain at different devices. So what we want is that our solution is as fair as possible in terms of battery drain at all devices, and that's what we observe. As you can see, the black bar here refers shows the fairness metric for the round robin scheduling policy. If we were to just take the 76 tasks, or in this example, in scenario 1, 75 tasks, and equally and create 5 equal chunks and give it to 5 different service providers, we don't appreciate the heterogeneity in their computing capabilities, and we don't appreciate the heterogeneity in their residual battery capacities. And that results in a very poor fairness metric. But if you look at first come first serve, the scheduling policy there is the faster device completes a task fast and moves on to the next task. So here there is an appreciation of the heterogeneity of computing capabilities, but no appreciation of heterogeneity in terms of battery capacities. So that again results in unfair battery drain. But if you look at our solution, which is the white bar at the end, it's able to appreciate the heterogeneity in computing resources, which means it distributes the tasks nicely, and at the same time keeping in mind the heterogeneity in residual battery capacity. So we achieve the maximum fairness possible. The next is we evaluated self-organization. Again, to quickly recap, by self-organization, uncertainty-aware self-organization, we just mean, okay, if you only believe the service advertisements, and if you don't, yes.
I have an online question, and I get, why is fairness the metric here?
Okay, so fairness is a very important metric in mobile grid computing paradigm, because when we are talking about an ad hoc deployment of mobile devices on the field, you want to maintain the heterogeneity of the resource pool. You want to maximize the network lifetime as a whole. So that's why fairness in terms of battery drain across all devices is preferred.
No, so if I understand that, just to jump in on behalf of the online questioner, who can jump in as well, though I don't know, they've not unmuted themselves, but feel free to jump in if you can. I guess the question I have is, if the goal here, I guess, because you're trying to minimize battery drain, is to keep the resource pool as large as possible. Is that correct?
Yes. Yes.
Okay. And as opposed to saying, hey, these devices are the most capable. So if I can get my from a strictly service requester perspective, fairness is not an objective. They want their task to be completed. Correct?
Yes. Yeah. That would. So for them, the best strategy would be the first come first served strategy, where in slide 30, if you look at the gray bar, that's what they are most interested in. Because if you would look at the response times, then first come first served would be the fastest, because the fastest devices consume more resource, consume more tasks. They finish a task and then they move on to the next one, and that way the fast devices end up doing more work than the slower ones. But that's not an intelligent strategy if you think about the longevity of the network as a whole.
Right. If you believe that tasks are going to keep coming in,
Yes.
over time, and you want to keep the maximum available pool alive, then that's correct.
Yes. So that's the reason why we go for a balance. And again, the self-optimization which we have built in for data parallel applications is keeping fairness in mind. As I said, we can always, tune the self-optimization module to have some other objective. It's possible. So you can tune it so that it mimics first come first served, or you can tune it so that it mimics round robin. Anything can be done, but the smartest strategy here in a mobile grid computing scenario would be to maximize the network lifetime. So moving on to slide 31, which talks about in which we evaluate uncertainty-aware self-organization. We are interested in seeing what happens, or what is the percentage of incomplete tasks that have to be forcibly migrated because the device died, a particular service provider died, in the sense it left, or it was shut off in the process of working on tasks. So if we were to believe, if the arbitrators have to believe the service advertisements completely, then you can see that when we increase the service provider churn rate, the number of, or the percentage of tasks to be migrated increases. But if we use these long-term statistics to decide on task distribution, then the percentage of migrated tasks is kept to a minimum. So that's the advantage that uncertainty-aware self-organization brings. So finally, moving on to self-healing, how much ever you optimize and you are proactive in handling uncertainty in the environment, there are going to be failures. And how do you handle those? So we introduce these concept of application waypoints, and what these waypoints do is they are like progress indicators. They say a waypoint conveys this is the residual task completion time, and I'm going to report to you in, say, the next 30 seconds. That's what the service providers are going to tell the arbitrator every now and then. And these application waypoints, if they are arriving at a very fast rate, it means there has been over provisioning, and the arbitrator tries to rectify it, because you don't want to unwisely spend on a lot of resources. There can also be under provisioning alerts when the application waypoints aren't arriving at the rate they are supposed to, and the leftmost indicates the ideal scenario where they are arriving at the correct rate and the application is proceeding towards its completion time in the normal manner. So the way we tested this was we took 4 devices with different residual battery capacities, and again we let the self-optimization module decide how to distribute tasks among these devices, and it chose one tablet, an Atrix phone, and the HTC phone to complete the tasks. But what we did was we simulated a device failure by shutting off the tablet, and this phenomenon was immediately captured by using application waypoints in the detection zone. And in the recovery zone, what happened is this additional device, even though its residual battery capacity is not the most optimal, it's very low, it was brought in so that the application deadline can be met. The deadline here was 120 seconds. So the second tablet was brought into service, and the system was able to complete the request on time. So this is how the self-healing module was verified. So now we took a detailed look on about the self-managing middleware. Now let's take a closer look about into the uncertainty-aware resource management framework. I was talking about task parallel applications, so let's start from there. So the previous example was a very simple data parallel application. We had, it was an object recognition application where the same task had to be performed on different chunks of data, so it was fairly easy. But what happens in a task parallel scenario like this? So what we did was we came up with a generic workflow representation. We used directed acyclic graphs to represent mobile application workflows. where the vertices represent the different tasks, which can be data collection, computation, and result generation tasks, and the edges represent the dependencies. So certain things that you have to note here are stage 0 is composed entirely of data collection tasks, and the subsequent stages can be data computation tasks, and the final one is result generation task. The salient feature here is the stage-wise. We deal with this workflow in terms of stages, which will come in handy later as I explain more. And you can see that there is a dotted circle in this illustration. What that is, it's actually a dummy task. So the assumption that we make here is there are no dependencies between tasks in one stage, which allows us to do things in parallel, and there are no dependencies across non-consecutive stages. So for example, task K23 directly connects to the result generation task, but we introduced a dummy task so that this workflow is balanced, so that it still allows us to deal with this workflow in a stage-wise manner. So to put this in context, let's take the application of ubiquitous, let's take ubiquitous healthcare applications or biomedical application workflows. At the bottom, you can see the different applications. They can be mood stress detection, alertness assessment, sleep quality assessment, performance assessment of an individual or a group. And you can arrive at all of these from biomedical signals collected using a plethora of biomedical sensors like electrocardiogram, electromyogram, breathing rate, skin conductance, temperature, blood pressure, and electroencephalogram. And the tasks in the middle, they can be either data analysis tasks, which purely deal with feature extraction from raw data, or they can be data manipulation or decision-making tasks, which can be like, by data manipulation, I mean artifact removal, noise removal, and decision-making is, using anomaly, performing anomaly detection, threshold-based anomaly detection, or decision tree analysis. So a particular example to make things more clear would be stress detection. This is a 4-stage workflow. As I already mentioned, stage 0 is purely data collection. And in stage 1, we can either, stage 1 is purely data analysis tasks, which concerns itself with peak detection, mean calculation, or power spectral density analysis. And in stages 2 and 3, we have data manipulation or decision-making tasks. If it was simply a stress detection application, then we'll just go for decision tree or threshold-based detection. But if you have to score the stress on a scale from 0 to 1, then we have to use some data manipulation, like weighted sum products, superposition, and so on. So uncertainty aware computing in the context of mobile application workflows. So if you have a mobile application workflow, what does uncertainty aware computing entail? The objective here is to generate a result that satisfies the application constraint in terms of the accuracy and the timeliness of the result. And when an application or a user submits a request, they're also going to specify what is the acceptable uncertainty in the result. So it's the responsibility of the arbitrator to achieve that objective, while at the same time determining the most appropriate workflow to use, the quantity and quality of data to collect from the sensors, and the computing resources to utilize. So it's basically a combinatorial nightmare for the arbitrators. So what we do is we came up with a two-phase solution, which is motivated by the following. So the choice of computing resources affects only the timeliness of the result, whereas the choice of models and data quality and quantity affects the accuracy as well as the timeliness. So what we do is we convert it into a two-phase procedure where we first determine the first fix the accuracy of the result, and then we worry about the timeliness of the result. So the way we are going to do this is by using leveraging interval arithmetic, and in stage 2 we are going to use multi-objective combinatorial optimization. So to go into the details of phase 1, as I said, the user or the application provides the acceptable level of uncertainty in the result, and this is given in the form of an interval, whose maximum width is gamma. So intervals are a very nice way of representing the the variability in a particular quantity. And as you can see in the graph below, so if we have to score the galvanic skin response or the blood pressure or the heart rate or the activity based on the data from the sensors, if we sample for a longer time, then the uncertainty in the score drops. This is pretty straightforward because the sensor output is a random variable. So if you were to look at the 95% confidence intervals of the sensor output, it's naturally going to reduce as you increase the sampling duration or you increase the number of samples. This is a very important observation because the variability in the final result that the user or the application asks for is heavily dependent on the variability in the sensor output. So as we said, we are going to deal with intervals. So the mathematics or the arithmetic is also going to be interval arithmetic. So what we do is we represent every workflow task as a combination of fundamental operations which are listed in the table here, which follow the rules of interval arithmetic. And we use these rules to propagate the acceptable level of uncertainty from the bottommost level, which is the final result generation task, up to the sensors. So once we know what the acceptable level of uncertainty is at every task, at every stage of the workflow, then the problem simply boils down to how much data do you have to collect so that the uncertainty doesn't go beyond the prescribed limit. So this transformation of the problem into finding the most appropriate sampling duration comes in very handy because it's very simple. All you have to do is perform a linear search of the best sampling duration that would give you that would satisfy the uncertainty requirement at every task, at every stage of the workflow, while at the same time not affecting the timeliness of the result. If you take the example in this slide, the sampling duration of 5 seconds satisfies the application specified gamma or acceptable level of uncertainty 0.05. Any sampling duration less than that is going to shoot the go beyond what the user or the application asked for. But if we keep sampling for a longer time, we are just going to spend more time without any major improvement in the quality of the result. So the trick here is to find the most appropriate sampling duration, and this problem, to recap, as I said, is basically a transformation of the original problem, which is you start from the acceptable uncertainty level from the final result, use interval arithmetic to propagate it up the workflow so that you know the acceptable level of uncertainty at every task, at every stage of the workflow, and then finally it boils down to finding the most appropriate sampling duration in stage 0, and that's what we do here. So once we have decided what the task sizes are, the task sizes are nothing but the amount of data that you're going to deal with at every task, at every stage of the workflow. Now the problem boils down to assigning these tasks to the different service providers in the field. Again, we can have multiple objectives and multiple criteria to do it, but by multiple I mean different objectives to do it. But what we want to do is to go for multiple objectives. We want to minimize the maximum battery drain at all service providers, and at the same time we want to minimize the maximum time taken by a computing device to do a particular task. This has a bearing on the make span or the time that it takes to compute the entire workflow. So we try to take care of both objectives. So when we do that, what we would have ended up doing is ensuring minimal response time while maintaining the heterogeneity of the resource pool. So it's very simple formulating this problem. It's you have two cost matrices capturing the cost for computing a task at a particular service provider, and in terms of battery drain and in terms of time. And the constraint here is very simple. A task can be allocated to one and only one service provider. So this is, even though it's fairly easy to formulate this multi-objective combinatorial optimization problem, it's difficult to solve it. So we propose a polynomial time heuristic, and it's a threshold-based heuristic. What the threshold-based heuristic does is it collapses the two cost matrices I was referring to, C1 and C2, into a single cost matrix with binary weights. And now the problem transforms into finding a feasible allocation with one cost matrix which has binary weights. And we call this algorithm a beta star algorithm because the feasibility here is the trick. So when we say we have to find a feasible allocation, what we mean is a task is allocated to one and only one service provider, and at the same time a service provider does not deal with more than beta star tasks. So the beta star here again ties to the Little's theorem concept that we were talking before, uncertainty aware self-organization. If we know that a node or a service provider is available for a particular duration, and if it's a large enough duration, then a number of tasks can be performed at that service provider, which means beta star will be high. But if the service provider availability duration is low, then beta star is going to be low. So that's where the beta star comes in. So as I said, we transform this multi-objective combinatorial optimization problem into a simple feasible allocation problem, min-max allocation problem, by collapsing the two cost matrices into one and just going for a min-max allocation. So again, to evaluate, we expanded our test bed and we implemented a bunch of functionalities, and we created three different types or flavors of workflows: a small workflow, medium, and a large workflow. And the difference between these was the number of stages, the number of tasks, and the number of task types. So as you can see, the task profiles, they are very different. They have very different profiles on the different devices. So what we did was we compared this multi-objective strategy against traditional single objective approaches. By single objective approach, what I mean is, if you were to only worry about battery fairness, or if you were to only worry about the make span or the time it takes to complete the workflow, how does it compare against the multi-objective approach? So you can see we are looking at two metrics. One is the make span, which is the time taken to complete the workflow, and the other is the fairness in terms of battery drain. You can see that the min-max battery, which was supposed to take care of only of battery drain, performs best in that scenario, and the min-max time performs best in terms of make span, because lower the time it takes, the better. But if you look at min-max battery in the make span graph, it's doing the worst. And if you look at min-max time in the fairness graph, fairness in battery drain graph, it's performing the worst. But our multi-objective approach strikes a balance. That's why initially we chose for a multi-objective approach in the first place. If we were to look at other metrics like total battery drain, in the entire network, and the communication cost incurred, min-max time incurs the least total battery drain, because to complete a workflow faster, you need to use the most efficient device in terms of time and battery, and naturally you're going to use devices that are faster and which are also very efficient in terms of battery. Like, for example, if you have to give a task to a laptop and a phone, the laptop is going to do it much faster and in a much battery efficient manner than what a phone would do. So that's what is reflected in this graph. So min-max time incurs the least battery drain, but remember it was very bad in terms of fairness in battery drain, as you can see on the right side of this, in the figure on the right. If you take the other metric, which is communication task, again, min-max time does the worst because it's using the most efficient devices and it's dumping all the tasks to those devices. So that's why the communication overhead or the number of bytes in the air incurred is very high. But min-max battery is comparable to ours in terms of these two metrics, but as we know, they are very poor in terms of the make span metric, as we have seen in slide 49. So in summary, the opportunity, we saw the opportunity that mobile devices are underutilized in an average, and we can exploit the heterogeneity in their sensing, computing, and communication capabilities for novel data and compute-intensive mobile applications. But there was a problem, which was if you don't handle the uncertainty together, they might propagate up the data processing chain and have an adverse effect on the result. And to that end, we proposed an autonomic mobile grid computing middleware to harness the heterogeneous computing, sensing, and communication capabilities, mobile application workflow representation to capture and convey these mobile applications in a manner that is understandable to the system. And finally, we also proposed data and resource uncertainty aware management frameworks to do things in an efficient manner. So here is a list of relevant publications. It's again available online in my webpage, which you can look up, and it'll also be in the video that's going to be uploaded on YouTube later. Finally, a note on future work. So some of you might have been wondering, okay, Hari has been talking about using mobile devices in the vicinity. Did he care about privacy at all? Yes, and we are working on it now. A common sense solution would be to categorize tasks based on sensitivity of the information handled, and maintain a list of authorized service provider for each category. Like if you're just doing a data analysis task, like extracting features, then there isn't much of a privacy concern because you're just working on a time series data. But if you're working on a data manipulation or a decision-making task which rates a person's heart rate, as a score between 0 and 1, then there is privacy issues, and those can be done only on personal devices, whereas a simple data analysis task can be performed on any device. So we are working towards a solution that incorporates this philosophy. And the other improvement is workflows. We were talking about acyclic workflows. So what happens in case of cyclic workflows, which is very common when you look at applications like distributed dictionary learning, which involves exchange between two workflows themselves, and which also involve a lot of iterations. So these are the things that I'm working on and I'll be working towards in the near future. So here is a list of relevant links where you can get more information about mobile grid computing at Rutgers and elsewhere. And I would like to take this opportunity to thank my co-authors and colleagues, Inkyung Lee, Ivan, and my professor Dario Pompili. And I would also like to thank colleagues at Cloud and Autonomic Computing Center at Rutgers, Dr. Parashar and his students, and DARPA and ONR for the funding. Thank you.
Thanks, Hari. I think we've just stepped over a little bit while people are thinking about questions to ask. For those that are about to run, and before we lose them, just remember that please provide feedback on the seminar in the survey, as well as join us for our next seminar on November 15th. More details, will come, when we end up here. But you can take a look at our website. So I guess maybe for those that have questions, please unmute yourselves and ask questions of Hari or send them to me by chat. I guess I'll begin with one, Hari. I guess the first question has to do with the one that I have is to do with scaling. I guess you talked about 10 mobile devices as being part of the sample. That was the mobile edge devices that were used in the study. Do you see your studies and the fairness metric and the empirical results you've observed? Would they change much to if in fact the number of devices were to go to thousands or to tens of thousands?
Okay, so yeah, in the interest of time, I didn't go into excruciating details, but we did test at scale, and we used simulations for that instead of using actual mobile devices. So here you can see for the different scenarios, we increased the problem and the pool size, and the way we could increase that was by using the simulator. So we did build a simulator which mimicked what the prototype did, and we tested out the simulations at scale. We scaled up to 30, 40 mobile devices, and it worked fine. But we did not test for 1,000 mobile devices because we are not looking at that scale yet. Even if it's a coffee shop, or a shopping mall, we are looking at 100 mobile devices maximum. It's not going to go to thousands when we talk about scale.
So what would your sense be, just as intuition, I guess, even though you might not have studied it at that scale, what does your intuition suggest for if you had tens of thousands of devices? Because obviously the attractiveness of what you're proposing is that everyone now has basically a computer in their pocket, right?
Yes.
And it's got, and I think that was the gist of your first slide, that there is 2.4 gigahertz of computing power with 16 GB of RAM and space that's there. How can I use it? And I guess what does your intuition suggest for scales at the numbers I was talking about?
Okay, so yeah, the number of participating devices or devices that would be using or be part of mobile grid computing will be at that scale. But it would be very difficult to look at metrics like fairness in battery drain because in such a huge setting, because if you increase the scale and size, naturally the dynamics are going to increase as well. The churn rate is going to increase as well. People might start charging their mobile phones in the middle. So it would be very difficult to arrive at a conclusion at a scale of 10,000 mobile devices. But my intuition suggests that if we were to, forgetting battery, forgetting all those dynamics, what my intuition suggests is that it's pretty difficult. It's pretty difficult to assess it at a scale of 10,000 devices. It's possible at a few hundreds. It would be difficult. So I was trying to delve into some pricing policy to those will be more interesting things to study at scale. What happens, or what is the usage pattern of what is the usage behavior when this scales to 10,000 devices. Those things would be interesting to study. How many devices, or how do people volunteer, or how much do people volunteer? Do they constantly hog the system, or do they also contribute to it? Those things, or those dynamics, would be far more interesting to study than just battery drain or the lifetime of the network. These analysis apply to a much smaller scale, in hundreds. That's what I feel.
I had a question.
Yeah, please.
What about security issues? If I allow somebody else to use my computer devices to do something.
Yeah, so there are multiple ways to go about it. One is using mobile virtualization to silo these applications, mobile grid applications that you are running for other users. And the only other way is to have only trusted software installed on your system. So the code will be provided by a trusted party. Only the data comes from data providers or data sources per se. And the code as such cannot do any harm. So it's fine if you number crunch even for garbage data, as long as you don't have unauthorized code running on your system. It should be absolutely fine. So security and privacy issues, as I was trying to point out, they are more common sense solutions here, where you just work with trusted devices and trusted code. That's pretty much it. So the most advanced thing that you can, the most complicated solution that you can think about here is mobile virtualization, just to silo, where if you have untrusted code, you run it there. Other than that, common sense solution of secure trusted code from a trusted party should be more than enough.
There's one question that has come in on chat. Does this you've shown applications that split into stages? Is that a requirement for this kind of mobile grid solution? Where the task graph, if it is represented as this DAG, is naturally stages, or are there other sort of non-structured applications that can utilize this mobile grid?
Okay, that's a very good question. I was rushing through the slides, so I couldn't elaborate it well. So yes, as of now, for now we looked at structured applications, which can be represented as DAGs with stages, tasks clearly defined, and so on. But as I was pointing out in slide 55, I'm pretty sure I'm still sharing the screen with everyone. There we are looking at cyclic workflows, where this structure of stages, the notion of stages is gone, and there is data exchange between multiple workflows themselves. So yes, we are looking to expand the capabilities of this mobile grid computing framework to be able to handle such unstructured workflows as well. But a little bit of structure is always required. It cannot be just one application cannot be just waiting, one workflow cannot be just waiting on something else forever. So that's why we brought in a little bit of structure, and that feature is going to be retained a bit, but not as stringent as it is now. But yes, we are working towards cyclic workflows, collaborative workflows, and to a certain extent unstructured workflows. It is possible. It is possible to expand, is what I want to say.
Thank you. Any further questions? Okay, I guess hearing no further questions, I guess Hari, I'd like to thank you very much for participating and presenting this very fascinating talk. We have a custom here in case you have not attended our previous webinars. All of you folks in attendance, please unmute your headsets and microphones, etc. And let's give Hari a warm virtual clap and applause for sharing with us some great ideas and insights in the area for mobile grid computing. Thank you, Hari, and I guess the slides and the recording will shortly be up on both the website and YouTube. And just a quick reminder, please do fill out your seminars, giving us feedback on how we can improve these seminars. And our next seminar will be on November 15th at noon Pacific time, and Professor Ethan Miller from UC Santa Cruz will be talking about Where Did My Photos Go? Challenges in Preserving Long-Term Digital Data. With that, thank you so much, Hari, and I'll see you all on November 15th.
Thank you, Sridhar. Thank you all.